So now we're gonna cover the aspect which connects the graph problem to the control problem. So as discussed before, we have graph problem where these states are symbolic, like state G, F, C, D. And the idea is that we find this value function, and once this is found, it becomes easy for us to navigate the graph in the sense that if we find us in a certain state, we can navigate to the final state by following the optimum path as given by the value functions. So now when we convert this idea to a continuous version, we see that this is replaced by this dynamical system where we say that the change in state is a function of the state we are currently in and a function of the control action taken. Now, J, as we saw here, is the total cost from traveling from our initial time t0 till tf, and then given the control function, so if you fix it or determine it, you can calculate the j or the cost that is associated with that control function. So in a sense, the idea is we are going from the graph problem where the states were symbolic to its continuous version given by this dynamical system, and we have this j function which helps us to define the cost. Now, one more idea that we would like to talk about is that this j is from time t0 to tf, as you can see here. Now, given that you're already in some state at time t, so you're in state xt, the cost from this state xt at time t to the final time tf would be given by this function. So the difference between this and this is simply that this is starting from t0 and this is starting from an initial state xt. So we are saying, okay, we are in xt, and from this state xt, we want to reach our final destination. Now, what I do is that if I minimize the right side of this equation, the right hand side of this equation, with respect to UTs. So what I mean to say is that out of all possible given UTs, I choose a UT which minimizes this, then my J would not be a function of U anymore because I have already determined and fixed the U for which this J is minimized. So I am writing this equation as this here. So J star is, given all controls, I choose the minimum one, then J star is given by this. So now what we have to look is that once we have the J star and it's going from T to TF, we will split this integral into two parts. We'll split it into T to T plus delta T and T plus delta T to TF. Now, once we write this as two parts, then we can segregate these parts together and write it together as J star of x, T plus delta T and T plus delta T. Because if you remember, when we had this J star x T to T, we were writing it because this expression is given like this. So if you just compare this expression to this, then you can understand that why I can write this as J star x T plus delta T, comma T plus delta T. Now, this is the principle of optimality. That's the reason why I am able to write this as this. Now, once I have it, I can view my J star as something of the value function. So you remember when we were doing the dynamic problem for dynamic programming, we had a graph, and in that graph, the way in which we decide which path to take dependent on what is the cost of the next step and the value function from there onwards. And we'll also compare the other alternative, that is the immediate cost and the value function from there. And then we find the minimum of u2 plus v2 comma u1 plus v1, and that was the way in which we were able to determine what was the value function. So in the similar way, this J star is defined from, or is defined as, you have some immediate cost, which is given by g d tau, and then you can add the value function from there on. And then minimizing over all of them would give you the J star. So this J star is nothing but the analogy of the value function. Now, what we can do next is we can see this expression and expand it with Taylor expansion. So what I can do is I can write this expression here in the Taylor expansion form. So it will give me a J star term, of course. Then it will give me a derivative with respect to time, a derivative with respect to x, and that's pretty much it. Now, the trick is that once it gives me the derivative with respect to time, I can just write this expression here as J star subscript t. Similarly, this can be written as J star subscript x, and this here is, if I take delta t to be very small and if I divide and multiply by delta t, then this expression here would become the derivative expression, which was a xt utt. So you see this comes from this, and then there was an extra delta t term which I put, so it stays here, and these are the remaining second order terms. So now what I do is the J star gets cancelled, well, because it has no dependence on ut, so this comes out of the minimum expression and this gets cancelled. So what we are left with is, inside the minimum, this because it depends on ut, this because again it depends on ut, this one got cancelled and this one comes out. So I can write my expression here as minimum of some expression plus J star t. Now what I do is I need to find the boundary value of this PD, and for this I write J star x tf comma tf as h x tf comma tf. Now remember, this is the same thing that we did for our graph problem when we said, okay, the value of the final state h is 0. So now we are saying, okay, the final state where we want to reach has some value which is given by this. So this is like, setting the boundary value condition of this PDE. Now let us define the Hamiltonian. So this expression, whatever is coming inside these curly brackets for minimization, we would define this as the Hamiltonian. So we will say, okay, let us define this as the Hamiltonian. And given this expression, once I find the ut that minimizes this expression, I will find it, substitute that ut, I'll call it u star t, which minimizes this expression in this part, and then I will get my Hamilton-Jacobi-Bellman equation. So what is this equation is, once I found out this ut, I substituted it, I got this form, and I added it to what was there before, if you can see here, and I get the Hamilton-Jacobi-Bellman equation. So very simple idea. This part of the equation remains same. This one I write it as my h, and then that's pretty much. So in this small tutorial, we derived how we went from seeing that there is a graph problem and it's continuous analog in the control version gives us this kind of Hamilton-Jacobi-Bellman equation.